Welcome everybody. Welcome everyone to this week's LPI seminar. We're really excited this week to be joined by Chi Ma from Caltech. Chi is a mineralogist and director of the analytical facility in the Division of Geological and Planetary Sciences at Caltech. He's the discoverer and lead investigator of 55 IMA-approved new minerals. There's even a refractory mineral called MgSiO₃-perovskite, which is an aluminum titanium oxide that was named in his honor. So today he's going to be sharing some of those discoveries with us. The title of the talk is Nanomineralogy of Meteorites, Discovery of New Minerals Representing Extreme Conditions of Formation. Thanks so much for being here with us this week, Chi, and I'll turn it over to you to share your screen now.
All right, yeah, thanks, Sam. All right, and all right, okay, let's start it. Thank you, Sam, for the introduction and for the invitation. A meteorite is like a book from outer space. When we take a closer look at it, we often discover something new and exciting. Nanomineralogy is the study of Earth and planetary materials at nanoscales, focused on characterize nanofeatures like inclusions, exclusion, donations, coatings, pores in minerals and rocks, and revealing nanominerals and nanoparticles. Here comes one example. Why is obsidian black? Because most obsidians contain nano-inclusions of magnetite. This is another example, rainbow hematite. Rainbow hematite has a thin film cover up on the surface of hematite crystals. The thin film consists of aluminum phosphate nanorods. So the rainbow color is due to the thin film interference. Nowadays, with high-resolution analytical scanning electron microscope, we are now capable to characterize solid materials easier and faster down to nanoscales. Nanofeatures are being identified in many common minerals and rocks, providing insights into their pyrogenesis and physical properties. New minerals and new materials with important geological significance are being discovered at micron to nanoscales. In SEM, electron beams strike a specimen, producing a spectrum of signals. Secondary electrons for topographic imaging, backscatter electrons for compositional contrast imaging, X-rays for elemental analysis, and lights for CL imaging, then diffracted electrons for structural analysis, and transmitted electrons for STEM imaging. We have this field emission scanning electron microscope at Caltech Geology. It's fully loaded with 6 electron detectors and EDS for fast elemental analysis, EBSD for structural analysis. EBSD is an SEM-based technique, has been intensely developed over the past 30 years. Now it's pretty mature now. The sample is highly tilted. Electron beam strike the sample, diffract the electron, and captured by this detector to display a EBSD pattern. EBSD is mainly used for crystal orientation mapping and mainly use EBSD for phase and application. So inside the scanning electron microscope, we also can do transmission EBSD. If we mount a TM sample in this arrangement, then we can do transmission EBSD. Then we may also use this electron detector for STEM imaging. All right, now let's look at minerals. So I will check this morning at a rough database. Now we have 5,829 IMA-approved minerals, most of them from Earth. So far to date, about 470 minerals have been identified in minerals. So updated by Anna Rubin and I in this book published last year. Our ongoing nanomineralogy investigation of Earth and planetary materials at Caltech since 2006 has revealed 55 new minerals from Earth to Mars and the early solar system, including 45 new minerals from meteorites. So I would like to start with episode 3. So my journey started in California. Bonitoite is barium titanium silicate from the Bonitoite mine, California. Bonitoite is a very beautiful mineral. It's the state gemstone of California. We use bonitoite as the barium titanium standard in the electron probe lab. So one day I came across 3 tubular inclusions in one bonitoite standard. This is one of the tubular inclusions. And it contains multiple phases. One is a new mineral, perovskite. This is the first new mineral I have discovered. Formula is barium 1, titanium 1, O3. Now zoom in. This brighter phase is perovskite along with bridgmanite here. Perovskite has this composition with minor silicon in the titanium side. Perovskite here is too small because it occurs at micron to nano size, too small for conventional X-ray diffraction analysis. So I used the EBSD for in situ non-destructive crystal structural determination. EBSD shows perovskite has an orthorhombic structure. Perovskite is one of the first new minerals approved by the IMA based on structural determination by EBSD. So this investigation helped pave the way for new mineral studies by EBSD. Actually, there are 2 more new barium titanate minerals here along with perovskite. The second one is this, barium 1, titanium 2, oxygen 5 occurs here. The third one is barium 1, titanium 3, oxygen 7 here. When I was writing up the manuscript on the perovskite for publication, I came across references from the 70s reporting that ultra-fine-grained barium titanate occurs in the matrix of Allende meteorite. So at that time, I wanted to do a comparison study to finish my paper. So I went to the Caltech meteorite collection and gathered 2 grains of Allende meteorite. This is one of them. So that was in January 2007. So now, 15 years later, I still haven't found even a hint of barium titanate in the matrix of Allende. But instead, I have discovered now 19 new minerals. All right, now present episode 1. Back to the early solar system. Allende meteorite is a CV3 carbonaceous chondrite, fell in Mexico in 1969. It's often described as the best studied meteorite in history. Our current understanding about the solar evolution is mainly based on intensive studies of components in this meteorite. Now, more than 50 years after it fell, Allende continues to be the source of new discoveries. Allende meteorite contains refractory inclusions, conjugates with a matrix bonding the rock together. Refractory inclusions are the first solids formed in our solar system. Now let's talk a little bit about mineral evolution. I really like this concept proposed by Bob Hazen. Now on Earth, we have accumulated more than 5,800 minerals. Now back to very beginning in the solar nebula, about 80 minerals have been identified, including 20 plus presolar minerals and 50 plus refractory minerals. They mark the very beginning of solar mineral evolution. 30 of the refractory inclusions were actually newly found since 2007, including 17 new minerals, 12 from Allende. Here are the 19 new minerals from Allende. 12 of them are refractory minerals. So here, allendeite, the scandium zirconium oxide, the hexamolybdenum is a molybdenum rich alloy, tistarite, titanium 3+ oxide, davisite, the scandium clinopyroxene, bridgmanite is titanium 3+ clinopyroxene, panguite is a special titanium rich oxide, conite is a special scandium rich oxide, pegmatite is a titanium rich silicate, bonitite is a vanadium rich clinopyroxene, bactite is a calcium vanadium aluminum oxide. Then rubinite is titanium 3+ garnet. Chitinite is another titanium oxide mineral. We also have 5 alteration minerals here from on the parent body. This is a ferrohibonite, the nuaite, that's a nickel germanium sulfide, and hutchinite, the titanium 4+ garnet, and the agenite, the chlorine-rich silicate, then butyrite, nickel tin sulfide. Actually, there are more new minerals from Allende are coming. Just stay tuned. Now let's look at some of them. Allendeite is the first new mineral I found in Allende. So it's a scandium zirconium oxide. It occurs here in this small ultra-refractory inclusion, along with hexamolybdenum. Now let's zoom in on this region. Allendeite occurs here, along with the cubic zirconia, perovskite, and those spherical osmium alloy. Allendeite has this empirical formula. EBSD shows it has a trigonal structure. Hexamolybdenum is a new alloy mineral from Allende. It occurs here along with allendeite. Now zoom in. These 3 euhedral grains are hexamolybdenum in contact with allendeite, spinel, and perovskite with those spherical osmium alloy. Hexamolybdenum has this composition. So EBSD shows it has a hexagonal structure. So the name is after the structure and the composition, hexamolybdenum. Molybdenite is the only phosphide mineral ever found in Allende. So it occurs here. Now zoom in. This is molybdenite. Just 1 grain is found. The name is after the composition, molybdenite. Davisite is a scandium clinopyroxene. The type of davisite is here, along with conite and perovskite and spinel. Bridgmanite is a titanium 3+ clinopyroxene. So the type Bridgman occurs here, along with spinel and perovskite sitting within the meteorite. Davisite and the gossamerite, they are not rare. They have been identified in many carbonaceous contrasts now. Okay, now let's look at panguite. Panguite is a titanium-rich oxide. It occurs within this ultra-refractory inclusion within olivine aggregate. Now zoom in. Here's a panguite sitting within davisite, surrounded by olivine. Now further zoom in. Here, those grains are panguite with the nearby two zirconium-rich panguite. Here's a davisite and surrounded by olivine. Panguite has this composition. It contains high concentration of refractory elements, zirconium, scandium, and yttrium. Showing this general formula. Here are the three EBSD patterns from the three grains here. Those EBSD patterns imply a cubic structure. Because panguite is also a brand new material, so we must use X-ray diffraction for structural refinement. So we use the synchrotron microloid diffraction. So energy scan by high flux X-ray was carried out at the advanced photo source in the Argonne National Lab on a 1 type grain at sub-micron resolution in the beamline 34. So here the X-ray probe strike specimen at 45 degrees. The detector is here. Synchrotron diffraction shows panguite has a orthorhombic structure, a subgroup of the Bixby type structure. This structure matches perfectly to the EBSD pattern. This plot showing the comparison of calculated and observed Raman spectra of panguite confirm its orthorhombic structure. If pangu were a cubic structure, we would only see one main peak here. The name panguite is after Pangu, the giant in ancient Chinese mythology, who created the world by separating the earth and heaven, the yin and the yang, from chaos in the very beginning, in allusion to the mineral with the ultra-refractory orange. So the name Pangu actually means ancient disk. This sounds like solar nebula, right? Next new mineral, kyanite, a special scandium-rich oxide. It actually occurs with type davisite here in this special ultra-refractory inclusion. The 4 grains here are kyanite in association with perovskite sitting in davisite. It has this composition. It's very rich in scandium, zirconium, and yttrium, and with a fair amount of rare earth elements above detection limit. Synchrotron diffraction shows kyanite has a chitin deficient Bixby type cubic structure. The structure might match perfectly to the EBSD pattern. Both panguite and kyanite, actually, they are not only new minerals, they are new materials. And when we look at those chitins, say they have a different valence, different size, but within the structure, they occupy the same chitin site. So it's very interesting. So nature has many advantages over technology on materials synthesized. So knowledge like of minerals like panguite, kyanite can be used to make advanced engineering materials. Next, tistarite is a titanium 3+ oxide. It was observed first in this refractory cluster within a conjure. Now zoom in. This cluster contains one Ti₂O₃, one TiO₂, and one titanium carbide grain, and with a bunch of corundum grains. This TiO₂ is actually rutile by EBSD. It contains nano inclusions of carbon and spinel. Okay, so this is tistarite, just one grain with a nearby titanium carbide and associated with corundum grains. So here is the oxygen isotope plot showing the associated corundum is plotted here on the CCM line. EBSD shows tistarite has a rhombohedral structure. Now let's take a closer look at this tistarite grain. Now I'm going to switch to high contrast backscatter electron image. This grain contains nano inclusions. The nano inclusions in tistarite is likely a new type of spinel. It's Mg titanium 3+ spinel. So later, a second tistarite grain were discovered in one series Allende section. Here, it's a titanium oxide grain. Now let's take a closer look at the grain. So the grain actually is showing some kind of contrast here. So the main region is a tistarite. The dark region actually is a rutile. Then we have a third phase. It's a new mineral, chitinite, titanium 3, oxygen 5. Chitinite has this monoclinic Fe₂SiO₃ type structure. This EBSD mapping shows we have two chitinite crystals here in contact with the tistarite and the rutile. All right, now let's look at a few new alteration phase from Allende, butianite and nuaite and butianite. Both occur in the fractures in this CI. Here the type nuaite occurs here, along with presolar. Meteorite has a very special integral superstructure in tetragonal symmetry. So here's a general formula for meteorite. Butianite has this general formula. It occurs within a fracture inside aluminum titanium dioxide. Hadronite is a titanium 4+ garnet. It's a new alteration phase found in Allende CIX3. It occurs here, along with other secondary minerals, monazite and presolar. Adrianite is a chlorine-rich silicate, also a new alteration phase from Allende CIX3. It occurs here, so it's just like several microns in size, along with presolar and monazite. All right. So after study Allende meteorite for a while, then I get Murchison from our collection, and for a close look for fun. So the first mineral I found is this chromium sulfide. So it's named after Murchison. It's called Murchisite. It occurs here. It's just slightly bigger than 1 micron within a olivine grain. The second new mineral we found is workite. Workite is a new ultra refractory mineral, and such a quad first observed this phase, then sent me for a close look. It took me several years to figure out what it is. So workite here occurs with conite, davisite, perovskite, and aluminum-rich diopside. So later on, we found the workite in several other carbonaceous chondrites. This is one workite in Vigorino Cb3 meteorite. It occurs here within this very small ultra-refractory inclusion. Workite here with perovskite. Here is a meteorite with a ring of davisite. So after the discovery of workite, so later on, we discovered the 3 other minerals. They have the same structure like workite. Now they are new members of the workite group. So bactite is calcium vanadium aluminum oxide. Then rdbischofite, the calcium aluminum oxide, and loose fuchsite, that's the latest member. It contains very enriched with Mg and titanium in this site. All right, let's take a look at them. Bactite, calcium vanadium aluminum oxide, occurs in a very special vanadium-rich Allende Ci. So here, along with hebonite and with other secondary minerals. Rdbischofite is only observed in one small CI from CH3 carbonaceous chondrite. It occurs here. So this grain here is rdbischofite in association with the hebonite and kieschurite. Loose fuchsite was first observed by Sasha Crot early this year in this CK chondrite. So Sasha then sent this mineral to me for a close look. Turned out, yes, it's a new mineral. So this loose fuchsite was just approved 2-3 months ago. All right, now let's move to the episode 2, return of the force, or should I say remains of the force. We have discovered 10 new high pressure minerals in heavily shocked meteorites. Bridgmanite is MgSiO₃ with a perovskite structure, was first discovered in the Tenhan L6 ordinary chondrite. All other 9 minerals are high pressure minerals from Martian meteorites. Now let's take a close look at bridgmanite first. Bridgmanite, MgSiO₃ is a perovskite structure, the most abundant mineral in Earth, now discovered in the Tenhan L6 ordinary chondrite. So Tenhan is the 3rd meteorite examined after Allende and Murchison. So it took my collaborator Oliver Schoner and I 5 years to track down this phase in Tenhan. It occurs within the shock melt vein. Now zooming on the SEM within the shock melt vein. So here's bridgmanite plus archimeteorite, and here nearby is nearby ringwoodite. Now zoom in. So those grains are a mixture of bridgmanite and archimeteorite. That's another region, bridgmanite plus archimeteorite. So bridgmanite here is about 50 to 40 nanometers in size. Meteorite is MgSiO₃ with an allendeite structure, revealed by EBSD analysis. But there's no EBSD pattern was ever obtained from bridgmanite due to instant electron beam damage. So finally, we did many synchrotron tries. Synchrotron diffraction finally reveals bridgmanite in this shock melt pocket along with Meteorite and remodeite. The type of bridgmanite here in Tinhan has this composition with a minor ion in the Mg site, also contains a trace amount of sodium and calcium. So bridgmanite and Meteorite. So here replace the precursor pyroxene crystals trapped within the melt vein. The associated phase assembly constrains the peak shock conditions to 24 GPa and 2300 Kelvin. This discovery concludes a half-century of effort to find, identify, and characterize a natural specimen of this important meteorite. Bridgmanite is a dominant phase in the lower mantle. Now let's take another look at this bridgmanite bearing shock melt vein. So here's a melt vein matrix. Melt vein matrix, let's take a closer look at it. This shock vein matrix contains many two phases. One is MgSiO₃. The other one is this special silicate called sphenoid silicate with this composition. So this composition is Mg₄, silicon 2, oxygen 7, right? So structure analysis by synchrotron diffraction shows this silicate has a tetragonal sphenoid structure. So its structural formula should be calculated based on the 4 oxygen. So here is the structural formula supported by the structural refinement by synchrotron diffraction. So we have an excess silicon in the Mg site with some vacancy. So this sphenoid silicate actually is a brand new to science high pressure phase. All right, now let's look at the high pressure phase from Mars. Decent Martian meteorite, the Shogatite, fell in Morocco in 2011. This is my first Martian meteorite I studied. Decent meteorite is heavily shocked. So here, this is 1 grain of decent meteorite. It contains those like dark domains. Those dark domains are shock melt pocket. Ahrensite is a high pressure mineral from Tisint. So it has like ferrite composition, but with a spinel structure. It type ahrensite occurs here next to a shock melt pocket. Here's an olivine with a surrounding pyroxene masculinite. Now zooming here. Okay, the type of ahrensite occurs here. This is a shock melt pocket. This region actually is bridgmanite plus wüstite. This bridgmanite identification was confirmed by synchrotron diffraction. Now further zooming. Ahrensite here occur actually as an aggregate of nanocrystals from like 50 to 400 nanometers in size. This is another occurrence. Those tiny crystals are ahrensite. So here the bridgmanite and wüstite next to the shock melt pocket. EBSD mapping shows the ahrensite nanocrystals has a random orientation. Ahrensite and the remoldite in tissant, a high pressure phase apparently formed by solid state transformation of olivine without much significant diffusion, given the preservation of Fe ion zoning from the original olivine. This is a quantitative X-ray map. Okay, next new minerals from tissant is tissintite. Tissintite is a high pressure clinopyroxene with a feldspar composition. Just think about it. Is a clinopyroxene with a feldspar composition. That means we need to calculate oxygen 8 to oxygen 6. That's why we have a quarter vacancy here. The type of tissantite occurs here. So now let's zoom in within this shock melt pocket. Those tiny crystals at micron to submicron size are tissantite. This is another occurrence. Tissantite is here, and the center region still is masculinite. It's another image showing the tissantite occur from submicron scale to nanoscale. Tissantite in tissant has this composition with a quarter vacancy in the M2 calcium sodium site. EBSD shows tissantite has diopside clinopyroxene structure. Tissantite being the most vacancy-rich pyroxene is brand new to science when we found it. Now, tissantite has been synthesized in the lab. Tissantite is found in rather common high pressure phase in lunar meteorite. Terrestrial tissantite is also found in impact structures on Earth. Plagial clays or masculinite with this composition from andesite to from albite to andesite may be shocked into tissantite type pyroxene by impact events. So the type tissantite is here. The type tissantite consists of half calcium ascolar component, that's this, and a quarter jadeite, and a quarter cruciurite. Okay, so how about tissantite with sodium higher than calcium? Then would be on this side. So here is a sodium analog of tissantite. So then there are very special jadeites. And I call them albertic jadeite. So particularly on this side, so this is a formula transferred from the albite composition. So with a quarter vacancy here, and about a quarter silicon in the alumina site. That's a albertic jadeite with excess silicon. I actually found this phase just several years ago in several ordinary chondrite. So here is an example. Here is a general formula for albertic jadeites with the excess silicon in alumina site. Here is one case showing the abiotic jadeite. Because in this special jadeite, we have excess silicon in the alumina side. So make this special jadeite is very unstable on the beam. So it's very hard to obtain electron diffraction. So finally, we also combined with the synchrotron diffraction, solve the puzzle. Now let's look at a new type of tissintite in Zagami marshy meteorite. So I call it tissintite 2 with this formula. So this formula is actually derived from this composition. So here is feldspar composition, and this is a pyroxene composition. So that's why this is a special tissintite. The type of tissintite has a composition of just feldspar. This tissintite 2 occurs in Zagami within this shock melt pocket here. Tissintite 2. Now zoom in. So tissintite 2 grows on the masculine light towards the shock melt pocket. It's another region, tissintite 2, on the masculine light into the shock melt pocket. Okay, in the same shock melt pocket, there's another brand new mineral here. It's called Zagamiite, named after Zagami. Zagamiite has this composition: so calcium 1, alumina 2, silicon 3.5, oxygen 11, with a hexagonal structure. Now let's zoom in, take a closer look. Zagamiite has this composition. So those fine-grained crystals are Zagamiite. Zagamiite actually crystallized from the shock melt with a mixture of many feldspar composition with a trace amount of pyroxene composition. Next high pressure minerals from Zagami is a libermanite. Libermanite has a K feldspar composition with a allendeite structure. It occurs here. Now zoom in. This is the type of libermanite is here with minor silica. Next one, stofluorite. Stofluorite is has andesite composition with a allendeite structure. Was first discovered in this marshy meteorite. That's a shocktite. It occurs here at the rim of shock melt pocket. So within the shock melt pocket, we have what Zagamiite here, and stofluorite occurs here, also here. Now let's zoom in on the green box. So stofluorite occurs here. Those tiny nanocrystals, they are stofluorite. They are very beam sensitive. So finally, we used the synchrotron diffraction, solved its structure. Okay, tennantite is the third new mineral found in tissint. It has this composition. It has a chromite composition with a CIF structure. So tennantite occurs within the chromite next to a shock melt pocket. Now zoom in, take a closer look. Those lamellae are tennantite within the host chromite. Now let's look at three new minerals from Sc₄Zr₃ marshy meteorite: schornerite, fayite, and leuite. all occurs within one iron titanium-rich cluster within this shock melt pocket. Now zoom in. So here it's schornite with ferrite and leweite. Schornite has O₆spinel composition, but with a CT type structure. And this is the structural formula. We can simply written as Fe₂TiO₄. Ferrite is here. The brighter phase is ferrite at micron size in association with schornite and O₆spinel. The ferrite has a formula iron 3, titanium 1, and oxygen 5. Ferrite has this Fe₄SiO₄ structure. So its structural formula is this, or simply we can written as Fe₃TiO₄. Leweite occurs here, like at micron, submicron grains, along with schornite and one-dot-deite. So leweite is Fe₃TiO₄ with a perovskite structure, whereas one-dot-deite is Fe₃TiO₄ with this lithium niobium oxide type structure. Leweite has this perovskite structure, and here is the empirical formula. Actually, it contains a fair amount of silicon in the titanium side. Let's make it really, really interesting. All right, so I finish here. So each new mineral has a voice, has a story to tell. I would like to thank my collaborators for joining me on this very exciting journey of discoveries. So discovery consists not in thinking new land, but in seeing with new eyes. Nanomineralogy is not a concept, is not only a concept, but also an approach for anyone dealing with solid materials. So field mission SCM with EDS and EBSD is my new eyes for nanomineralogy investigations. Okay, I stop here. Thank you very much for your attention.
All right, thanks so much, Chi. People are allowed to express their appreciation through clapping like that and through in the chats as well. For those of you with questions, you may either raise your virtual hand and I'll ask you to unmute yourself, or you can type that into the chat box and I'll read your question to the speaker for you. Just to get us started, I have just a quick question about sort of the applicability of all these high pressure mineral phases, nanomineral phases that you've identified. I imagine just because this is happening during impact, it's pretty much instantaneous formation of a lot of these phases. But despite that, could you still use pressure, temperature, phase diagrams for these to maybe put some constraints on the energy of impact or other petrologic conditions like that?
Yeah, this is an excellent question. Yes. And say our phase diagram normally is based on a simple component, right? And with some like ideal composition. And the beautiful things when we study those natural heavily shocked meteorite or terrestrial impact rock, is impact process is such a dynamic process. And our rocks, original rocks, is a different porosity, different composition, and so make it make it just a real such a play field for me to finding those new high pressure phases. That means they were never synthesized before.
Yeah.
For example, tissintite was not synthesized before. Since the 70s, people doing high temperature, high pressure experiments, right? To like say, basically to squeeze every common minerals, right? To say what happened at a certain GPAs, certain temperatures. They would break down, right? But tissintite was not synthesized before. So now, a few years ago, I gave a talk at Stony Brook, and a graduate student then really interested in tissintite, and she decided to synthesize it. So she did it actually. She did synthesize the tissintite in a lab. So later on, now we found the tissintite actually not everywhere, but rather common. For example, very common in lunar meteorites, very, very common. Also very common on terrestrial impact rocks. Now, when we know what it is, we just see them, it's everywhere. So the other one is mentioned, as I mentioned, for example, the albertic jadeite. So the bunch of papers published, let's say from the high temperature, high pressure experiments, when we compress the albite, it would break down into ideal jadeite plus silicon. And this was also observed, I think, one or two cases in natural shock meteorite. But when I started to study this phase, I said, where's the silica? I just cannot find it. Where's the silica? No, the silica actually is still within the jadeite structure. It's a very special jadeite. So this special albertic jadeite, based on the mineral rule, is not a new mineral, but it's a brand new high pressure phase because it never synthesized before. So it's just kind of total new to science. So that's make it exciting. I'm sure now some people doing high pressure, high temperature experiment are going to pick up like albite to say whether they can turn that into albertic jadeite.
Yeah, you're just giving us all sorts of good ideas. Well, thanks for answering the question.
Right. So sometimes it's really hard to constrain the conditions, like shock conditions, temperature, then durations, then complex composition of your original compositions, they all kick in. So then building a real like space diagram is really difficult. So far, they're only like estimates, I would say.
Yeah. Oh, hey, that's good. That's plenty of work. Keep us busy.
Right.
I'll move on to the next questions from Micah Schabel. You can go ahead and unmute yourself, Micah, if you're still there.
Hi there, Chi. My name is Mike Schabel. I'm a research scientist at Georgia Institute of Technology. I've done a little bit of this materials characterization and sort of the microscopy stuff, well, less on the microscopy side of things, but I have maybe a bit of a silly question for you, but given that these phases are so small, how do you even know where to look on the samples? How do you know, given these black and white images, that this is something interesting? And then from that, how can you understand, given that this is, maybe only in a couple of places, what the sort of typical abundances of these really trace phases are, so that we could then use those in models to say, this might have been, something about the formation conditions, petrology.
Right. So, okay. So it's okay. Thank you for asking. Yeah, this actually is kind of important because I'm a trained I'm a meteorologist. Okay, working now in the field of meteorite. So it's a kind of no return for me, down to earth now. It's okay. So when I look at a rock, like say, immediately I want to know what are mineral phases there. So now, of course, because we have a field emission SEM, we can easily tune the machine down to nano resolution. then to study those things. So sometimes, like say, assume we have like say micron-sized crystals with nano imaging, then those micron-sized crystals would be crystal clear, right? For us to study them. And so that's why I always telling the like users or students, like say, no matter what solids, what rock you are dealing with, even millimeter-sized crystals, you want to do a nano investigation to that nanopores, nano donations, all those things. Sometimes those nanophase at the grain boundaries, they are normally common than we think. So also I like to enjoy to study those famous rocks. So that means that tons of study already done on it. Now you see, wow, this cannot be explained. Then that means there must be a story. Then to some researchers may say, oh, this is how bizarre. Now we cannot explain this anymore. But to me, it's such a beautiful work. Now, yes, there's a story behind that. It's up to us to figure out what it is. So regarding those nanophases, like I say, they're so nano, so rare. Why they're kind of important? We don't really care. And no, say, quite often when we examine a rock, we obtain those essential information from accessory phase rather than from like feldspar, quartz, pyroxene. So we need like accessory phase like zircon, apatite, right? There's the dating info, all those things. So for example, like say like Davisite, conite I mentioned, so they can contain really high concentration of rare earths. So we all do rare earth analysis, like say bulk samples. Sometimes just a few grain of those minerals can throw that pattern off. So that means for a complete study, we want to have those rare earth patterns from individual phase, right? Then we can do a comparison. Some are more primary, some we know they are later stage. So yeah, if we just rely on bulk analysis, we might miss some important points. Yeah, so that's me. Basically, so when you use high resolution, check your rocks, any rock, so it's quite often you're going to run into something new. Yeah.
Great. So actually kind of taking your point, there's a comment here from Graham Neslin, says spectacular intricate studies. I can only find analogy in geometallurgical studies of micron scale platinum group metals in these copper and nickel sulfide ore deposits. And that's, I think, just to add my own input to that as somebody who's been really interested in those particular phases. Your comment about, looking at how the origin of these things, whether they're from precursor materials or whether they're actually from late stage reactions, I think can actually provide some really interesting insights into the petrogenesis of some of these rocks. So just a comment, I suppose, there.
Yeah, thank you.
So there's another question here, sort of a question about, the question says, in the impact of a meteorite, are the effects varied throughout the meteorite? So I think maybe if I can paraphrase you here, this is from Paul Grout, by the way, just translating nanomineralogy to more macro scale, I guess, interpretations. How does that vary across the sample, I suppose?
Right. Today I just really say go fast on those just try to show off more new minerals, and then I think most of the new minerals already published, and with the detailed discussions and interpretations. If you're interested, definitely you can just Google the mineral name. You can find those papers. Otherwise, you can always shoot me an email. Google my name, shoot me emails. I would be happy to provide you papers or manuscripts. Yeah, so it's yeah, it has been a lot of fun, and I would say they are important for us. So I mean, to study meteorites from a mineralogy point of view is important, and combined with cosmochemistry analysis. Yeah. Great.
And we have one, I think, more question here. I think it's one you've perhaps addressed already, but just very quickly for our users before we run out of time. The new nanominerals discovered were found in shock meteorites. How likely is it that these new nanominerals may be found at meteor impact sites on Earth? This is from John Littleton, and I think you touched on this already, but just as a reminder.
Yes, it's a really important. Yeah, okay. So after study those shock meteorite, and also I'm getting involved to study like impact rock, like from Greece impact structure and rocks from Canadian impact structures. And yes, the tissintite is common. It's there, and just somehow, I mean, the early studies just somehow missed them. So when I look at like a rock, so I want to know who's who. So what I'm looking at from a mineral point of view, like say, what it is. So now, because we have EBSD, such a powerful tool for us to electron diffraction, so we can see it for sure. So sometimes, for example, I study meteorite A chondrite, actually it's called Ti₂O₃ A chondrite. It contains silica phase. So then I say, what silica? So I use my EBSD to examine it. Actually, it contains 3 types of silica. It contains quartz, tridymite, and cristobalite, 3 of them. So that's me. Normally, we can easily miss it. Sometimes if we identify quartz, I say, oh, we assume all the silica there would be quartz. Yeah, if we take a closer look at it, now it contains 3 phases there. So then, of course, that totally changes our interpretation of the meteorite. Yeah.
Absolutely. That's funny. We were just having a conversation about that in our experimental petrology group of somebody had, found a paper saying like, oh, they found tridymite in this meteorite. It's like you go through the literature and it's just like people just assume whatever silica phase that they've seen elsewhere, but no one actually has looked at the structure or anything like that. So it's important for petrogenetic interpretations.
Yeah, that's right. Normally in my papers, like say, when I write down some mineral name, I have a structure to back it up.
We appreciate that. If there are any other questions, feel free to ask them now. I'll give a few seconds for people to do that. And in the meantime, I just wanted to say thank you again, Chi. It's a fascinating talk. Love hearing about your work and all the fascinating discoveries that you've made. And yeah, you're going to keep our experimental people busy trying to reproduce a lot of these phases.
Yep, yeah, it's my great pleasure. And thank you again. Thank you, Sam, for the invitation. Yeah, it's my pleasure. Yeah.
All right. Well, if there aren't any other questions, I'll leave people to continue their congratulatory remarks and appreciation in the chat box, and invite you all to come again next week. We'll be talking about stable isotope fractionation, so a bit of a deviation from this topic. But you're all welcome to come back next week, and I look forward to seeing you all there. Thanks for coming, everybody. And Chi, thank you again.
Yeah, bye.
Bye.